Okay, so today we are going to set up FreeRTOS for our project. We mentioned that we will be using FreeRTOS. So we are going to set it up from scratch from their repo and implement it in our project so that we can use the core API functions without the STM32 middleware, which I think is cleaner to use. The raw FreeRTOS API functions are cleaner to use than STM32 ones, but whichever you prefer, you can use them. So I'm going to go to FreeRTOS and GitHub and then search for their repo, this one right here, and then go straight into FreeRTOS kernel, copy the link, go to the root of our software project and clone it here. So this is going to be Git. Okay, now it is done cloning the repo. You can go ahead and go ahead with. So you can see it right here. The repo is right here on the root of the project. So what I'm going to do is I'm going to open it in STM32 cube IDE. This is the project right here. So open project. If I expand it, you should see the FreeRTOS kernel here. So then the next thing I want to do is we are going to clean up some of the parts of the kernel. The first thing we clean up is the compilers. So we only need one compiler. So you're going to go into portable, and then you can see all these compilers that are included. So we only need GCC and this memory man. This is the memory manager. So basically it has the heaps that are used by FreeRTOS. So these are the only two things that we need. So I'm going to delete everything else apart from those two. So it depends on which compiler you're using. Delete the ones that you're not using. So I'm going to delete that, and then these up to this point. Delete. Okay. So next we go into memory manager, and we are only going to be using the heap 4 for dynamic memory allocation. So delete all these other memory managers. Delete that. Delete that. Okay. Next is come here and refresh the project. Fresh. So in portable, you should only see GCC, and memang we have heap 4 only. Now the next thing, go into GCC, portable GCC, and then you can see now all these chipsets that have been, or rather the cores that have been set. So we are using STM32 F401. So if I do a quick search here, STM32 F401, this one right here. I wanna show you the core that we are using. So let me look for this one. Yeah, it's a Cortex M4 core. Cortex M4. So anything that is not ARM Cortex M4 here, we don't need it. All right, so we are going to look for CM4, which is for Cortex M4. This one, CM4F, and then delete everything else. So you're going to delete from that point up to this point. Delete that. then delete from this point to this point, delete. Okay, so that should be good. So we go to our IDE, obviously we hit refresh here, and GCC we only have ARM-CM4, so we have two files, port C and port macro H. Those are going to be all that we need. Now what we do next, we try to build the project. Let's build the project and see what happens at this point. So build, right click, build project. Okay, 0 errors and 0 warnings. Now what we have done, rather what we have not done, is we have not added this kernel to the compilation path of the build process. So what you do, you go to make it visible to a compiler, we go to project properties, includes. So we add every file, every folder that has a header file at this point. So we go to add is a workspace path, click on workspace, go to your FreeRTOS kernel. The first one is obviously the include folder. This has all the includes you need, so add that. Okay, okay. Then the other file that has an include folder is a header file, is a GCC. Is this file right here, GCC. There's a header file right here, so we add that. So add workspace FreeRTOS kernel, and go to portable GCC, this folder. So select the folder, not the file. Click OK. Click OK. The next thing we add is the source locations. So source locations, add folder, go to FreeRTOS, portable GCC ARM4. There's a source file there, and then you can see, if you look clearly, you can see C files on the root of the kernel itself. So all of these are source files, so we are going to add the root of the kernel itself. So add folder, the kernel itself. Okay, okay, click apply, then apply and close. Okay, so let's try to build that project. So build. Right, so we expect a bunch of errors here. Now the first thing that we have is the FreeRTOS config file. So this file is not included in the kernel file. It's included in the FreeRTOS core repo or folder. So if you come to your GitHub repo, the FreeRTOS GitHub repo here, and go back one step, you'll find this FreeRTOS folder. Open that. So open that, come to FreeRTOS, then demo. Then now here we look for the chip or the folder that has a chipset that is closest to what we are using. So you can see all these are AVR chipsets. Then you have Cortex A5, A9, A whatever. We are using M4. So you look for Cortex M4. it doesn't have to be specifically close. I mean, specifically the same as what you're using. As long as it's the same family of M4, it'll be the config file will be okay. So I'm using STM. So core Cortex STM F1. There is STM F30. I mean STM32L. This is 103. Looking for STM32 F104. Let's see. So there are so many. Let me start from the bottom, going up. Cortex Smart Fusion 32L, F107, 100, simulator, 3 Nordic, M4 STM32, Cortex M4F STM32 F4. I think this should do the job. So open that, and then this is the file we need. This one right here. So this is just a bunch of configuration defines. You can set 0 or 1 to activate or deactivate some features of the kernel. So I'm going to copy this file. So Control A, Control C. I come here to my project. Remember last time we said that we are going to be using a cleaner editor. So I created this main application source code just to separate the application file from this other bunch of files. So I come to include, I right click and create a new header file. I'll call it new file, and it's called FreeRTOS config.h. Finish. Then paste that. Save. Okay, so let's try build the project again and see what errors we get. So anytime you get error, it's advised you start phasing one by one. You fix from the top going down. And now you can see now we are recognizing the FreeRTOS config.h file, but now we have a new error which is system core clock undeclared. So this is system core clock is in the line 52. So it's right, line 52 is right here. So if I hold control and click on this folder, I mean on that line, you can see that it is the system core clock variable is available, but it is not being seen by the compiler. So what I do, since this is inside a different file, I just need to make the compiler see that this variable exists, and the way you do that in C is just declaring an external variable. I just make this file make this file consume a variable that is not inside its scope. So just do that and tell it that it is the variable exists by using the external keyword. So we build again. All right, so this is a warning that we'll fix it later. Okay, good. So you can see now we have new errors down here. These are first defined. Okay, first defined here in C basically means that you have two definitions of the same function. So basically, you can see this is SVC handler and SV handler, and these are interrupts. These are mostly interrupts in the STM32 world. But Since you're using a kernel and the STM32, both of the STM32 has defined these files and the FreeRTOS has defined these files. So that's why they are doubly defined. So we have to shut them down in the STM32 side. So these are interrupts, and you can see, if you look closely, you can be able to see the file that they are defined in. Yeah, this file here. This is STM32 IT. Even though this is an object file, but it's the interrupt file. So what you do, you come here to your core source. This is where STM32 stores its interrupt. So open that file. So we are looking for, let's see, console. We are looking for three functions: SVC, PendSV, and SysTick. So you can see this is PendSV. They are right here actually. So what you do, you can delete them or you can comment them. So I prefer to comment them out. Comment them out and comment not that one. See, where is it? This one. PendSV and SysTick. Save. Obviously, the next thing we build again and check whether those errors still exist. All right. So new errors, application task hook, undefined reference to tick hook. So we want to disable these hook functions because we are not using them at the moment. So they are defined in the config file. These hooks, idle hook, tick hook, they are used for preemptive scheduling procedures inside the kernel, but we don't need them at the moment. So you can set them to 0. So any hook you set it to 0, just set that to 0. This is another one, you set it to 0. And check for stack overflow, set it to 0 too. Build again. Okay, multiple definitions of main. Okay, it's a common error. You can only have one main function per project, per C project, one entry point. So it means that it shows here, if I look closely, there's a kernel example, CMake example. So there's an example that has a main.c file that probably, no, that definitely has a main function. So that file is in which folder? Let me see. Example CMake example main.c. So if I open, where is it? FreeRTOS kernel examples. Okay, so I've opened the main application folder in a different editor. So I'll include freertos.h file here. Let's just see whether that builds correctly. So build project here. Should build with no errors. All right, good. So it means we can use the FreeRTOS API functions here. Okay, so I'll do this. This is the main function. So you can create a task basically and test whether the it's going to compile correctly. And then next time we can upload and check the hardware itself. So now when you're creating FreeRTOS tasks, there's an API function called xtask create. So I'm gonna do that right here. So create task test setup. So when you create a task, it returns either true or false, but in FreeRTOS lingo we call it PD pass or PD fail. So I'm going to create a like a boolean type. Okay, so base type t status. It's 5 minutes. Base type t status. Then you say status equals x task create. The first parameter to s task create is the task itself. So I'll have two things here. I'll have a function prototypes. So because C doesn't have hoisting, so I have to define a prototype to tell it what to expect. So I'll have a static void x task. The name of the function will be, the name of the task will be task. I can call it test task. Then it takes a void pointer parameter, pv parameters. Okay. Then down here, I can say function definitions. So I implement that function static void. Let me just copy it. Copy that, paste. Then every task is like a small infinite loop inside itself. So I create an infinite loop. So your code runs there, and your function variables just come right here before the while loop. Okay. So this is what you are going to use to create the task. So you have to create this task inside the core. So we paste that here, and then from the documentation of the FreeRTOS, I just open this guy right here. You can see it traces the code, task code, task name, stack depth, parameters, priority, and then the handle to the created task. So this is going to be, you can use a name if you want, but basically for debugging purposes. Task. Next thing was the stack depth. So stack depth in words. So I'm gonna say 1024, and then the next one was parameters. No parameters null. Let me reduce the size of this. Priority, then created task. So priority can be 1, and then the handle null for the moment. You can use a handle if you want. You'll use them later for suspending and resuming tasks, but right now they let them remain null. So next we check if it was created. Okay, so if status is equal to pd pass, pd pass is like true, it's like true. So we can have a message there, else another message. So what I'll do, I'll create up here. You can have private variables, create a message buffer. So jar message buffer, let's say 50 bytes. It's a size of 50. So I want to put messages into this. There's a more elegant implementation of that using log files and events, but I'll just say as printf into message buffer, task created. Okay. And then this is sprintf. Copy this, paste, task failed. Okay, save that. So sprintf is in the standard header. So what I'll do, I'll include it before that. I'll include stdio.h. All right. So later on, we can be able to send this message into, this message to print to the console. Okay. But for now, we just want to test whether that task was created. Okay. So after creating tasks, the next thing you do is you start the scheduler that starts running those tasks. So it's v task start scheduler. Save. Okay, so I will create and start the scheduler or the scheduler. Okay, let's compile that and see whether it runs. Whether it compiles in the first place and fix the errors that we have. If it compiles, you're good. Next time we can upload the code and test all those other things. But for now, what error do we have? RAM overflowed. These are very nice error, but I'm going to show you how to fix it. Okay, so you can see we have this error that says, where is it? BSS will not fit into RAM. So the RAM has been overflowed by 13,736 bytes. So this means there's something that is occupying our RAM. Most probably, I don't know. So, okay, first of all, the BSS section is a section used to store variables, statically allocated variables that have not been initialized. So it initializes them to 0, right? So the good thing is that STM32 provides a memory analyzer, so we can actually see what is taking this much of our memory, our RAM memory. Now, for us to be able to do that, we need to be able to compile the software and produce an ELF file, okay, X file for use. So what we do, you come to this linker script right here, this LD file. If you scroll down, it contains definitions of memory sizes, what goes to which region of memory, and the most important is this part right here. So if you look closely, you can see RAM is defined from this address to occupy 64 kilobytes of memory. So what I'm going to do, and the flash is 256 kilobytes. Obviously, remember, if we look at the STM32 F4, you can see it has what? I'm looking at the RAM. Where is the RAM listed? 256 flash and 64 KB of RAM. Okay, this is 4 kilobytes. Now what I'm going to do for me to be able to compile, I'm going to increase this to, let's say, 96. They increase it by 32 kilobytes, 96 kilobytes, save, and then build the project. So when we build, we should be able to see, we should be able to produce a hex file that you can analyze. You can then analyze and see what is consuming our memory that much. Like it's actually depleting the whole RAM for some reason. So let's wait for it to build. Okay, good. So it builds. If you go to debug, you can see we have this is our hex file. Now you go to Window, Show View, Build Analyzer. It's down here. So you can see these two memory regions. So memory regions, you have the RAM and the flash. So you can see I've set it to 96 KB. It's showing here. I'm not interested in the flash at the moment, but the flash is like 6.5% that is occupied, but this is occupying 80% of 96 kilobytes. So I go to memory details, go to RAM, and you can see this is occupying the largest size. This is 75 kilobytes BSS section. So go down there and look for whatever is holding the largest memory size. You can see these are bytes, 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 until we get to this guy, which is a heap. So the heap is occupying 75 kilobytes. Now, if you go to FreeRTOS config file, remember we chose heap4 as our heap. So if you go to FreeRTOS config file right here, you can see something called config on line 57, config total heap size. You can see 75 times 1024. This is 75 kilobytes of heap size. So actually it's going away with, it's consuming all our RAM. So we reduce that and set it to, what I'll do to solve it, I'll reduce it and set it to 10 kilobytes for now. 10 kilobytes, save the file, and then we set back, or we reset our memory size to 64 kilobytes. So come down here and set it back to what it was. This is 64. Okay. So let's see whether we are able to build that. Okay, we have some warnings here. Okay, we are able to build. We're able to build the project successfully, which is a good thing. So next time we'll get rid of these warnings and upload the code to the microcontroller, and then we're ready to kick off. We're ready to start creating tasks, creating the mission code, logic, software, state machines, file managers, housekeeping functions, a lot of the framework basically that will go around the project. So see you next time, and if you have a question, leave it down below. Okay, bye bye.